In the previous session, we discussed about a stable mode of operation of 555 timer. There, we derived the expression for frequency of oscillation. Now, let us continue the topic. Now, let us define duty cycle. Duty cycle is defined as on time period by total time period, where total time period is on time period plus off time period. Therefore, duty cycle denoted by D is given by D equal to T on by T on plus T off, that equal to T1 by T1 plus T2, where T1 equal to 0.69 into RA plus RB into C, T2 equal to 0.69 RB into C. Substituting these values for T1 and T2, we get D equal to RA plus RB by RA plus 2RB. Percentage duty cycle is given by RA plus RB by RA plus 2RB into 100%. In this astable mode of operation, we always get percentage D less than 50%. For this square wave, the duty cycle is always less than 50% because on time period depends on the charging condition of the capacitor, in which both RA and RB are taking action, whereas in discharging time period, that is off time period, only RB is coming into picture. So, in applications where we require symmetrical square wave, that is duty cycle exactly equal to 50%, there we have to modify the circuit. The modification required is very simple. Connect a diode across RB, and this diode should be connected in such a way that the diode short circuits the resistor RB in the charging time period, that is only RA comes into picture in charging time period, whereas in discharging time period diode is reverse biased and it opens the resistor RB. Therefore, in discharging time period only RB enters into picture. Therefore, if we make RA equal to RB, then we will get on time period equal to off time period. Therefore, duty cycle equal to 50%. Let us consider the circuit. Adjustable duty cycle rectangular wave generator is as shown in figure. Here, diode D1 is connected across RB. During charging time period, the diode D is forward biased because of plus VCC, then it short circuits the resistor RB. Therefore, charging time period T1 equal to 0.69 RAC. During discharging time period, the diode D1 is reverse biased because of the voltage across the capacitor. Therefore, it acts as open circuit. Now, the discharging time period is given by T2 equal to 0.69 RBC. Therefore, total time period T1 plus T2 equal to 0.69 into RA plus RB into C. If RA equal to RB, then we get percentage D equal to 50%. Now, let us consider the applications of astable mode of 555 timer. First application is FSK generator. Here, the FSK term indicates frequency shift keying. This is one of the methods used in digital communications of carrier modulations. Here, the FSK means the carrier frequency shifts between two frequencies. This is because in digital communications we have to transmit the data which lies only between two digits, they are 0 and 1. We have to send the information in terms of only zeros and ones, and in order to transmit it in wireless communications we have to shift these bits to high frequency ranges. For that one, carrier modulation is required, so FSK comes into picture. So, the carrier frequency changes in accordance with the amplitude of the modulating signal. Here modulating signal is having only two levels, that is either 1 or 0. If 1 is the carrier frequency, will be at one frequency. If 0 is present, then carrier frequency shifts to other frequency. Now let us consider that circuit. The FSK generator circuit diagram is as shown in figure. Here for the Astable Multivibrator, we have added some more circuitry across the resistor RA. Here to the base of the transistor Q1, the input digital data is applied, which is of the form zeros and ones. Here simply it is indicated as square wave with 150 Hz. Now when input is high, the PNP transistor Q1 is open circuit. Therefore the 555 timer will work with a frequency f equal to 1.45 by RA plus 2RB into C, because the transistor Q1 is open. Now when the input is at low level, then transistor Q1 is in on condition, that is it acts as short circuit. Now the resistor RC comes in parallel with RA. Therefore the frequency of oscillation is f0 prime equal to 1.45 by RA parallel with RC plus 2RB into C. This frequency is high as compared to the previous frequency. This is mainly used in teletypewriter using modems, where the required frequencies are 1070 Hz and 1270 Hz. So by selecting proper values of RA, RB, C and RC, we can make this application. Now let us consider another application, that is pulse position modulator. Pulse position modulation is one type of baseband modulation. Here the position of the pulse is varied in accordance with the amplitude of the modulating signal. Here our modulating signal is square wave, but in this application let us consider a triangular wave, and how the pulse position changes let us consider in detail. The pulse position modulator circuit diagram is as shown in figure. The modulating signal is applied to the control terminal 5. Output is taken from pin 3 as usual. Here the modulating signal, let us consider it varies as a triangular waveform. Now when the modulating signal voltage is applied, what happens to the circuit? First of all, let us consider without modulating signal. When VCC is applied, as per the internal diagram of the 555 timer, we will get the reference voltage for the upper comparator as 2/3 VCC, for lower comparator as 1/3 VCC. Now let us consider VCC equal to 15 volts for example. Then upper comparator reference voltage is 10 volts, lower comparator reference voltage is 2 volts. Now if modulating signal is applied, if an amplitude of the modulating signal equal to 2 volts, then it will be directly connected to the upper comparator reference voltage terminal. Therefore the upper comparator reference voltage becomes 12 volts and lower comparator reference voltage also changes, now it becomes 6 volts. Then due to this positive voltage, first of all the initial condition of the 555 timer as astable mode is that in the discharging path, instead of reaching up to 5 volts, when it reaches 6 volts, then itself it changes state, because now the lower comparator voltage reference voltage is 6 volts. Then it will be in the on condition, that is the pulse duration condition. Now it depends on the upper comparator reference voltage. Now it is 12 volts. Now until the charging voltage across the capacitor reaches 12 volts, it will be in on condition. When it reaches 12 volts, it becomes low. Now let us consider the control voltage is at 0 volts. Then what happens? Instead of coming up to 6 volts, it has to wait until it reaches 5 volts. So as the modulating signal changes, the pulse width and its position also changes. During positive half cycle of the modulating signal, what happens? the pulse on time period increases and off time period decreases. During negative half cycle of the modulating signal, the pulse on time period decreases and off time period increases. In this way, the pulse position changes in accordance with the modulating signal. Now, let us consider another application, that is Schmitt Trigger. Here, Schmitt Trigger is nothing but a bistable multivibrator. Here, the Schmitt Trigger consists of UTP and LTP points. That is, when sinusoidal signal is applied to the Schmitt Trigger circuit, then we will get a square wave output. Here, the UTP and LTP points are determined by the 555 timer, and they are taken as the 2/3 VCC and 1/3 VCC, that is upper comparator and lower comparator reference voltages. So, if we connect external circuitry in such a way that the input signal voltage average value is at the midpoint of 2/3 VCC and 1/3 VCC, that is VCC by 2, then we can simply convert sine wave into square wave. Schmitt Trigger circuit is as shown in figure. Here, the threshold terminal and trigger terminal both are tied together and input voltage is applied to it through a DC blocking capacitor, and at this junction point of tied point of threshold and trigger terminals, we are getting a DC voltage, fixed voltage of VCC by 2 due to the external arrangement of R1 equal to R2 equal to 100 kilo ohms. Now, the input sinusoidal signal is having average value at VCC by 2. When the input voltage reaches 2/3 VCC, then the output changes its state and comes to the lower value. It waits until the discharging voltage reaches 1/3 VCC. It happens at the 1/3 VCC point of input voltage. Now, at this point it changes to the high value. So, in this way high to low change occurs at 2/3 VCC and low to high changes occurs at 1/3 VCC. Therefore, sine wave is converted to square wave and it is having the same frequency as that of sine wave. Now, let us start another topic, that is phase locked loops. First of all, let us consider the importance of phase locking. For that one, let us take up an example. Here, in communications, we want to transmit the information signal. This information signal should be compatible with the channel. For that one, it should be modulated. So, when it is modulated, we require a carrier to modulate it. The carrier frequency must be constant irrespective of the aging of the components used in that carrier generator, that is oscillator, or with respect to temperature, or with respect to humidity or atmospheric changes, or with respect to vibrations, etc. With respect to all these changes, the carrier frequency must be stable. Otherwise, at the receiver we cannot decode the information transmitted. So, we have to get a carrier which is having stable frequency. For stable frequencies, we all know that we have to use a crystal oscillator. The crystal oscillators, that means we have to use a crystal in that oscillator. The crystals are available only for certain frequencies. Otherwise, on special request, we have to get a crystal from the manufacturing company. So, it is very difficult, whatever frequency we want for the carrier, we cannot get at that instant of time. So, there is another way of getting stability of the oscillator by phase locking. So, here by phase locking phenomena, the free running frequency of the oscillator is stabilized with respect to variations in the aging, temperature, humidity or vibration, etc. and etc. So, let us consider the basic principles of the phase locked loops. The basic block diagram of the phase locked loops is as shown in figure. It consists of phase detector, low pass filter, amplifier and VCO. The phase detector is basically a multiplier and produces sum, that is Fs plus F0, where Fs is the signal frequency, F0 is the VCO free running frequency, and difference, that is Fs minus F0 components at the output. The low pass filter removes the high frequency component Fs plus F0. The error amplifier amplifies the low frequency components Fs minus F0 and applies the signal as control voltage Vc to VCO, that is voltage controlled oscillator. The signal Vc shifts the VCO frequency in a direction to reduce the difference frequency Fs minus F0. When VCO sets Fs minus F0 equal to 0, then Fs equal to F0 and the signal is said to be phase locked. So, as per the block diagram, we are having a free running voltage controlled oscillator whose free running frequency is F0, and if the signal frequency Fs is applied to the phase detector as one input, the free running frequency of the VCO is applied as another input to the phase detector. The phase detector, as already said, gives sum and difference frequencies, that is Fs plus F0, Fs minus F0. Next, succeeding stage of the phase detector is low pass filter. So, it passes only the difference frequency. Here, if the difference is very large, then the low pass filter does not pass even the difference frequency. So, the low pass filter passes if the difference is small. Then the difference frequency at the low pass filter output becomes input to the error amplifier. The error amplifier amplifies this signal and gives average value as voltage to the control terminal of the VCO. This controlled voltage at the VCO terminal leads VCO free running frequency, that means it increases or decreases the free running frequency in such a way that Fs minus F0 is 0. So, when this occurs, we say that that means when Fs equal to F0, then we say that the circuit is under locked condition, and when the difference frequency is small and low pass filter passes the frequencies, then at those frequencies, even though these two frequencies are slightly different, we call that the circuit entered into the capture range. After entering into the capture range, we get the surety of getting the phase locking within a short time interval. After getting the phase locking, the circuit will be having a stable frequency, that is Fs equal to F0. There may be slight difference between Fs and F0 with respect to phase only. So, this phase variation may be adjusted within the circuit. Okay. So, here this circuit is having three types of actions. One is free running, next one capturing, next one locked. After locking, the circuit keeps the VCO frequency always stable. Figure shows the capture transient. As capture starts, a small sine wave appears. This is due to the difference frequency between VCO and input signal. The DC component of the beat drives the VCO towards the lock. Each successive cycle causes the VCO frequency to move closer to the input signal frequency. The difference in frequency becomes smaller and a larger DC component is passed by the filter, shifting the VCO frequency further. The process continues until the VCO locks onto the signal and the difference frequency is DC. Now, let us consider important definitions related to PLL. They are: 1. Lock-in range. The range of frequencies over which the PLL can maintain lock with the incoming signal is called the lock-in range or tracking range. The lock range is usually expressed as percentage of F0, the VCO frequency. Capture range, the range of frequencies over which the PLL can acquire lock with the input signal is called the capture range. It is expressed as percentage of F0. Pull-in time, the total time taken by the PLL to establish lock is called pull-in time. Now let us consider individual blocks of the phase locked loop. First of all, let us consider phase detector. As it is already mentioned, phase detector is simply a multiplier. It multiplies the input signals and gives sum and difference frequencies at its output. There are two types of phase detectors. One, analog phase detectors. Two, digital phase detectors. First of all, let us consider analog phase detector. As shown in figure, analog phase detector is simply an electronic switch. The switching action is controlled by the VCO voltage. The VCO voltage is usually a square wave. So, during on time period of the VCO voltage, the switch is closed, then output voltage of the phase detector is equal to the input signal voltage. If VCO voltage is at low level, then switch is open, then output of the phase detector is 0. As shown in figure B, VCO output is a square wave. Let us consider the input signal is a sinusoidal signal which is having the same frequency as that of the VCO signal, and here the input signal frequency is having the same frequency, but also it is having the same phase, that is phase difference between these two signals is equal to 0. Then the switching action occurs as a half wave detector. Here it passes only positive half cycles and the error voltage is positive. If the phase difference between the input signal and the VCO signal is 90 degrees, as shown in figure D, we get the dashed portion as the phase detector output and error voltage will be equal to 0. And as shown in figure E, if the phase difference between VCO output and input signal, if it is equal to 180 degrees, then the phase detector passes only negative half cycles and the error voltage is negative. Therefore, this type of detector is called a half wave detector, since the phase information for only one half of the input waveform is detected and averaged. Analysis: a phase comparator is basically a multiplier which multiplies the input signal by the VCO signal. If VCO signal V0 is given by V0 sin 2 pi F0 t plus phi and input signal is given by Vs sin 2 pi Fs t, then the phase comparator output VE equal to k times Vs V0 sin 2 pi Fs t sin 2 pi F0 t plus phi, where phi is the phase shift between the input signal and VCO output and k is the phase comparator gain. After simplification, we get phase comparator output VE equal to k Vs V0 into cos 2 pi Fs minus F0 into t minus phi minus cos 2 pi Fs plus F0 into t plus phi at log Fs equal to F0. Therefore, VE equal to k Vs V0 by 2 into cos minus phi minus cos 4 pi F0 t plus phi. The first term in this equation represents DC and the second term represents high frequency, which will be filtered by the low pass filter. Now this DC voltage is directly proportional to cos phi and it is also directly proportional to Vs. Therefore, we can conclude that the drawback of this type of analog multiplier is that VE is non-linear. Now, let us consider balanced modulator type phase detector. Balanced modulator type phase detector is as shown in figure. The error voltage, that is phase detector output, is taken in between two collectors terminals of Q3 and Q6, and input voltage is given at base terminals of Q1 and Q2. The VCO input is given at base terminal of Q3 and Q4 tied together, and Q4, Q5 tied together. Now, when input signal is square wave and VCO signal is also square wave, then we get the error voltage, that is phase detector output voltage waveform as shown in figure. Here, average error voltage can be written as 1 by pi into area A1 plus area A2 as shown in figure. Here, 1 by pi into area A1 is written as IERL into phi plus area A2 is replaced by minus IERL into pi minus phi. That is equal to IERL into 2 phi by pi minus 1. That equal to 4 IQRL by pi into phi minus pi by 2. That equal to K phi into phi minus pi by 2. Here, if you observe this equation, we can say that error voltage is directly proportional to phi, that is, it varies linearly with respect to phase difference. The variation of DC component of phase detector output with respect to phase difference phi for this balanced modulator is as shown in figure. It linearly rises from minus IERL to plus IERL. In this session, we considered several applications of astable mode of 555 timer. Then we considered the phase locked loops, its importance and basic principle of operation of the phase locked loop. Then we started in giving the details of each block of the phase locked loop. There we started with the first element as phase detector. There we considered the topic, that is analog phase detector.